Hello, my name is Tulani, and I present our work co-authored with Jennifer Trinh, Alomran, Jennifer Clayton, and Professor Zhang. The authors are with the University of Nevada, Reno, USA. The title of our work is Design and Characterization of a Word, an Active Wearable Assistive and Resistive Device. The presentation will be arranged as follows. I will start by giving an introduction and motivation of this work. After the introduction, I will outline the project goals. I will then talk about the choice of actuation mechanism. Specifically, I will provide a brief overview and advantages of twisted string actuators. I will then talk about how TSAs allow the usage of supercoiled polymer strings. After that, I will then talk about the design of a word, the considerations made, and the components that form a word. Finally, I will talk about the different characterizations that were conducted on our word, and then I will discuss the conclusions and future work. The ubiquity of wearable robots devices have been steadily increasing over the last couple of decades. Partly this is because wearable robots have shown key benefits in providing assistance in rehabilitation, resistance and strength training, and in augmenting human capabilities in performing challenging tasks. While the advantages provided by wearable robots in the previous slides certainly improve our lives, it is even more desirable to have devices that combine those functions. First, combining these functions reduces the number of required independent devices. Second, devices that possess dual capabilities can be life-saving. For example, for astronauts, resistive mode is useful for strength training during space travel, which limits the detrimental effect of muscle atrophy. Assistive mode is useful during spacewalk, limiting hand fatigue and allowing for longer spacewalks. However, combining these functions into a single device is difficult. First, increasing the degrees of freedom of devices generally increases the device size and weight due to the increase of actuation units. Second, actuation mechanisms that are compact and allow for increasing functionality tend to produce limited force outputs, which limit useful device output. Lastly, it may be challenging to incorporate required sensing mechanisms. With the motivations from the previous slide, the project goals were divided into two. Firstly, it was to design a compact, lightweight, and soft wearable robotic glove that possessed assistive and resistive modes. Secondly, it was also to characterize the force output and motion of the glove in order to demonstrate the performance in different conditions. It suffices to say that the device is driven by twisted string actuators. So, what are twisted string actuators? TSAs convert rotative motion of a motor to linear motion by twisting two or more strings as shown in the video. In this video, the direction of travel is parallel and in line with the motor placement. The TSAs were selected for award for a couple of key advantages. First, TSAs lead to high force amplification from low torque motors. This means that reasonable resistive forces can be produced by these actuators. Second, TSAs have a compact form factor. Low torque motors are generally not geared, which means that their footprint is generally small. Therefore, TSAs have a low footprint. Thirdly, TSA strings as a motion transmission uses string and as a consequence are a compliant actuator. However, since TSAs require strings to twist for actuation, embedding the strings into soft fabric of a glove becomes tricky. In addition, when large diameter strings are embedded on soft fabric, the friction between the strings and the glove is increased. The compliance that TSAs provide by using SAP strings for motion transmissions than DS can be further improved. TSAs allow for the use of strings of different properties like diameter, conductivity, and stiffness. For example, supercoiled polymer strings or SCPs are silver-coated nylon strings that are conductive and stretchy. The SCP strings can be used as TSA strings, improving the properties of the actuation mechanism. When SCP strings are used in TSAs, they increase the compliance of the TSA mechanism. In addition, since they are conductive, the SCP strings allow for position sensing. The SCP strings were chosen for use due to the extensive work that our group has done in this area. Some of our past work has investigated how the actuation range of the SCP strings can be increased by applying rotations in addition to voltage actuation. In addition, a transient model was developed for the self-sensing of these SCP strings. When SCP strings are used as TSAs, the force output is the main consideration. To ensure that our ward was compact, lightweight, and soft, the following choices were made. First, compact, low-footprint sensors were selected. High-range force-sensing resistors were used. Further, the combined SCP strings were used as TSA strings and also provide position sensing. Second, a soft glove was chosen to increase comfort. Thirdly, the threading designs were selected to minimize the deformation of the fabric when forces were applied, allow for coupling of fingers, and increase fingertip forces. Lastly, a microcontroller that was compact but possessed high clock speed and number of input-output pins was selected to enhance compactness. Now I present our ward, as seen from the picture. Our ward uses 6 TSAs to achieve finger movements. 4 of the 6 TSAs uses both stiff strings and SCP strings and are utilized for finger flexion. The remaining 2 TSAs consist only of stiff strings and are used for the extension of the fingers. 4 FSRs are installed at the fingertips. It is noted that the thumb does not have an FSR. Our ward weighs 198.1 grams with actuation unit, but without the power supply. The thumb was not actuated for this version of the device. Before the characterization of our ward, it was necessary to validate the sensing performance of the sensors. Specifically, here we show the performance of the SCP strings both for length change and resistive change when used as TSA strings. As shown, varying motor rotations in the setup above result in change in length and resistance of the TSA and SCP strings. Since the FSR is widely available, the sensing and calibration setup is not shown. To characterize the motion of a ward, a motor rotation ramp input was used with the motor rotations monotonically increasing and then decreasing. The resulting pictures on the right show the motion of a ward due to a similar input. The figure at the bottom right demonstrates that varying the rotations changes the length and the resistance of TSA strings and SCP strings. The static force characterization of a ward was conducted by choosing 3 positions, P1, P2, and P3. As shown in the picture, P1 was when the finger was almost fully open, P2 the finger was halfway open, and P3 was almost fully closed. These positions were repeatable and attained through the motor rotations shown in the table on the right. In the figures, the white arrow shows the direction of the tension applied to the strings, and the red arrow shows the direction of movement of the finger when the tension is applied. For each position and each finger, the force test was repeated 3 times. The figure on the left shows that the stiff strings produce higher forces than SCP TSAs. Since the TSAs with stiff strings is used for resistance, higher forces were desired. The compliance of the SCP strings reduced the force output of the SCP TSAs. The summary of the results are shown in the table on the right. Sigma is the standard deviation computed from the 3 trials performed from each position. In addition to the static force test, dynamic force testing was conducted. In this experiment, different loads were attached to the fingers and then it was actuated. As demonstrated in the video, high loads were actuated, further showing the resistive capability of a ward. In conclusion, in this work, we have presented an assistive and resistive glove that is compliant and compact. We have further characterized the motion and force output in the static test and in dynamic experiment. In the future, force feedback control will be analyzed and implemented. In addition, user studies will be performed to test the effectiveness of the resistive mode of the device. Thank you. For more details, please see our paper, which is number 333. I'll be happy to take any questions.